In the LR circuit, we shall discuss growth of current first. Let us consider an inductor and a resistor connected in series, and it is excited by the battery. We have a switch named K having positions 1 and 2. When the switch K is in position number 1, the battery is connected to the series LR combination. Whatever potential that battery delivers, some part is developed across inductor and some across resistor. So this is Kirchhoff's voltage law. Now, the drop across inductor can be written as L into d dt of I of t plus R into I of t, that is Ohm's law, equal to the total battery potential. This equation can be rearranged by dividing the whole equation by R, and we shall substitute E upon R, which is voltage upon resistance, that is always equal to current, equal to I0. This is called as the steady state value of current. This is the only tricky thing we are doing here, and by substituting E by R equal to I0, our equation looks like L upon R d dt of I of t plus I of t equal to I0. Now our intention is to find I of t, which is inside the differentiation, and one term without differentiation. So this is a first order ordinary differential equation. We shall use the simplest technique, that is separation of variables, and here we shall have current terms separated on left hand side and time terms on right hand side, and the values of R and L, these are the constants, so not to be bothered much. Now I have only multiplied this equation by -1 so that I can fit the integration formula properly, and the integration is integration f dash upon f dx is equal to log of f. So here I0 is a constant steady state value minus I of t, so is a functional quantity, and the derivative of I of t is -1, which is accommodated here. So integrating both sides, we get log of I0 minus I of t equal to minus R upon L times t into K1. K1 is a constant which can be evaluated from the boundary condition, and boundary condition is our physical situation. At t equal to 0, we place the switch at position number 1, and that is the time of the experiment beginning situation, and I of 0 is equal to 0. So there is no current at the time t equal to 0 when the switch is placed in the position 1. So substituting I of 0 is equal to 0 in the above equation, we get K1 is equal to simply I0. Substituting K1 equal to log of I0, we get the last equation which is appearing on the screen. Now collecting the terms together, we have log of I0 minus I of t on left hand side. We can carry this log of I0 on left hand side and take exponential on both sides. We get I0 minus I of t upon I0 equal to e to the power minus R upon L times t. So just a simple rearrangement will make a complete solution of what we were trying to evaluate, that is transient current in the circuit. So the equation in the red bracket appears I of t equal to E upon R, which is I0, into 1 minus 1 upon e to the power R upon L into t. So we shall just discuss this equation in detail. Now we shall discuss these cases one by one. Let us consider the first one, t equal to 0. So for t equal to 0, I of 0 is 0, and that was our physical situation. Let us put it into the equation that we have found out as solution of the ordinary differential equation. So that becomes E by R. You can simply understand that t is being replaced by 0, and e to the power 0, anything raised to 0 is 1, 1 upon 1 is 1, and 1 minus 1 will be 0. So we arrive back at to the physical situation with which we have started, so everything seems to be quite okay. The second situation is t equal to infinity. It means a steady state condition where time is quite long, and for large value of t, we have to consider this equation. So I of infinity is equal to e upon r. Now t in this equation is being replaced by infinity. E to the power infinity will be infinity, and 1 upon infinity will be 0, and 1 minus 0 will be 1. So we are left with I0. That is the steady state value of the current, which we have defined E by R. Now the third and the most important case we are going to discuss, t equal to L upon R. So in this equation, t is to be replaced by L by R, and by doing so we have e to the power 1, and the value of exponential is 2.718, and you can work out the reciprocal of 2.718 and subtract it from 1. So we get 0.632 I0. That is the value t equal to L upon R, which is called as LR constant of the circuit, and that defines the time in which current rises to 63.2% of its maximum value. Now we are in position to plot this equation. Before plotting, we shall consider the battery potential to be 1 volts, simple situation. We shall consider resistance 1 ohm, and obviously E by R is 1 ampere, and we shall prefer value of inductors 0.5 Henry, and L upon R appears to be 0.5 seconds. So it means that it will take only 0.5 seconds to rise the transient current to 63.2% of its steady state level. Now for value of E, R and L we shall have a plot. So this plot is developed in Maple, and you can see at 0.5 seconds 63.2% of the maximum value of the current we have reached. Now we shall consider the decay of current. Now under the situation when steady state current is flowing in the circuit, we flip the switch from position number 1 to position number 2, and this is the time where our experiment begins, and at this moment the current in the circuit was I0. Now applying Kirchhoff's voltage law, battery voltage is 0. This is the potential across R, and this is the potential across induced EMF across inductor. So this induced EMF will collapse through the resistance R. The differential equation of the circuit is L into first order time derivative of I of t plus R into I, that is by Ohm's law. This is equal to 0. This is again ordinary differential equation of first order. We shall divide this equation by R so that we can reach to the similar form, and here at t equal to 0 we consider that I0 current was flowing in the circuit, and that was the time when we flipped the switch from position 1 to position 2, and separation of variable technique we have to use, and I of t we want on left hand side and tt term on right hand side. So our differential equation will take this form. Now a simple integration will give us solution of the differential equation. Now integrating on both sides, again same integration formula we are exploring. Log of I, which is function of time, is equal to minus R upon L times t plus K2. K2 is the constant of integration, and for t equal to 0, I of 0 is I0, that is steady state value. So substituting t equal to 0 will diminish this term, and K2 will be simply log of I0. Substituting that, we get solution of the differential equation. Now we can take exponential on both sides. I of t minus I0 is equal to e to the power minus r upon L times t. So I of t is equal to I0 into e to the power minus r upon L times t. This is solution of the differential equation. Now we can discuss in different time zones, like in the earlier case. Now at t equal to 0, I of 0 is equal to e upon r 1 upon e to the power r upon L into 0. So we have replaced t by 0. Anything raised to 0 is 1, and this is I0. E by r, that is I0. So we have arrived back to the boundary condition with which we have started. So this is the first glimpse that our solution is correct. Now for large time, I of infinity, t is being replaced by infinity. So e to the power infinity will be infinity, 1 upon infinity will be 0. So for steady state, this current will vanish. Now the most important case, t equal to L by r. So this will make e upon r 1 upon 2.718, that is 0.367 I0. Now this is defining LR constant of the circuit, and it will take this time L upon R. This time takes 36.7% fall in the value of current. So that is how we define LR time constant. It will take 0.5 seconds again to decay the transient current in the circuit to 36.7% of its steady value. So this is a plot of the solution, and here you can see the mark that for 0.5 seconds the 36.7% of the fall in current. Thank you. This is the circuit in which primarily voltage was applied to L and R. For growth of current, we have I of t equal to, see here, capital I is not permitted. So while writing the mathematics mode, I have explicitly used small I, and for the very purpose I have used small I in the PowerPoint presentation also. So L into DIFF derivative, first derivative with respect to time of I of t, will generate this equation number 1. This is named as ODE1, and the boundary condition is I of 0 is equal to 0. We are assigning our output at solution 1, and simply we are exploring the command dsolve ODE1 for BC1. So it returns the output like this. As we have discussed, E equal to 1, R equal to 1, L equal to 0.5 Henry. Here solution takes this form, and by definition L upon R is 0.5 upon 1. So it will take only 0.5 seconds to rise the current to 63.2% of its steady state value, and plot right hand side of solution 1 1. Solution 1 1 is solution 1 only, where E equal to 1, R equal to 1, L equal to 0.5 is substituted, and this is that equation being considered for plotting. And you can look at the grid. At 0.5 seconds it takes 63.2% of the steady state value. We can choose something else also. E equal to 1, R equal to 2 ohms, and L equal to 0.002 Henry. So these values are substituted in the basic solution, which was called solution SOLN1, and L upon R is 0.002 by 2, that will give 0.001. So here we have plotted up to 2 seconds, and in 1 microsecond the 63% value will be raised. And let us look at the plot of solution 1 2. We can have a grid to see that in 0.001 seconds the maximum 63.2% of the maximum value is achieved. You can just get into the detail of this. So this is the value which is steady state value is 0.5, that is E upon R. Now for decay we have this quantity 0, and ODE2 we are defining L into DIFF of I of t plus R into I of t equal to 0. So here steady state value I of 0 is equal to I0, which is E upon R, and we are just exploring D solve ODE2 for BC2, that is boundary condition 2, where with the same solution, and we can substitute E equal to 1, R equal to 1, L equal to 0.2 in solution 2, so that we can study the transient current in the circuit. And it takes 0.5 seconds for decay to go up to 36.7% of its steady state value. Similarly, we can opt the second set of values of constant R equal to 2 and L equal to 2 millihenry, and it will take 1 millisecond time to decay the current to 36.2% of its maximum value. So here this is the plot. You can see the two plots at one time. So this is the growth and this is decay for first set of data, and for second set of data you can look at the time value. This is the growth and this is decay.